So there's one more topic I would like to do, which is suppose we have a thin walled vessel filled with a pressurized fluid. And this is something which is quite common in LPG cylinder which you have can be treated to be something like this, which is a fluid inside with high pressure. In fact, a lot of containers which move, they move like this. So here we are looking at the analysis when the wall is thin. That means we look at a vessel of radius r and wall thickness T. And what we mean by a thin walled vessel is T is much less than R. We can extend the analysis to thicker wall vessels. There we will have to take R1 and R2, two radii, but we'll just look at this case. Now here, if we denote the axis by X and the other two directions as Y and Z. Now, you may see books where the axis may be called as Z. So it really doesn't matter. So if I look at an this is an element on the wall. I look at a small element on the wall. Now obviously this element will have a slight curvature. It is an element on the wall. It's a curved this surface. So let's say the stresses here are sigma 2 and sigma 1. So the blown up picture is something like this. So here sigma 1 is the circumferential stress, the stress along this theta direction. Sigma 2 is the axial stress. Now on the wall outside, if I look at this element, sigma r will be 0. It will be just because of atmospheric pressure. So that if we take it as 0 or gauge pressure as 0, then sigma r will be 0. Now on an element like this, all components of shear stress will be 0 because there is axisymmetry. If shear stresses will not be 0, they will deform and axisymmetry will be distorted. It will not stay. So because there is an axisymmetric problem, if you go in one direction, they distort in one direction. If you go in the other direction, it will distort in the other direction, and that has to be uniform. So therefore, there will be no shear stresses. That means what we can say are here, because there are no shear stresses, sigma 1 and sigma 2 are the principal stresses. Now sigma 1, which is the circumferential stress, this is also called as hoop stress. And sigma 2, the axial stress, is also called longitudinal stress. If we look at an element which is cut by the xy plane, we look at half the element of the cylinder cut by the xy plane, and we look at a small element of this which has delta x length. So now on this face, we will have sigma 1, this thickness is T, this is delta x. So this force will be sigma 1 T times delta x. Similarly, sigma 1 T times delta x is the force here, and because of the pressure, if I do a force, I cut a section and I do a force balance. So because of the stresses, the force on the wall of the cylinder is sigma 1 T delta x on both the walls, and the pressure will exert a force which will be equal to the pressure on the projected area P times 2R times delta x. Okay, and these two must be equal. They are acting in opposite directions. Pressure is acting inwards. Sigma 1 is like this. So therefore, what we will have is sigma 1 into 2T into delta x minus P into 2R into delta x is equal to 0. So therefore, what we get is sigma 1 is equal to P times R by T. So because of the pressure, the circumferential stress which comes on the element is equal to P times R by T. And this is for a thin walled element. Otherwise, you will have to account for R1 and R2 being different, and then still you can do the analysis. So, but we are just looking at. So this is sigma 1, and If I cut a circular section like this, then this stress is sigma 2, and sigma 2 times 2 pi RT is the force which is coming. Now I cut the section in the YZ plane. So therefore this circular section, this force is equal to sigma 2 into 2 pi RT. And what is the force due to pressure? So what is the area on which this pressure is acting? The radius is r, so it will be p times pi r square. Actually, it is p times r inverse square, but since the wall is thin, so we'll have to. So from here, what we get is sigma 2 into 2 pi RT and from here what we get is sigma 2 is equal to PR upon 2T. The axial stress is equal to the pressure multiplied by the radius by 2T. Okay. Now this is, 2 pi RT is approximation because it's a thin wall, it's the area for the thin wall. If it is not thin, then you have to take the full area. Okay. I'm just doing this for this case. Okay. Now, suppose if this cylinder is to fail because of shear, if it is made of ductile material, which means it fails because of shear, then what do you have to find? You have to find the maximum shear stress which is occurring in any plane. Okay? So how do you find that? So then we use the Mohr circle. Let's first plot the total. We have this situation. So now if we plot the Mohr circle for this stress configuration. As somebody rightly said, it will be at an angle of 45 degrees. You can find it from 45 degrees. But the easier way or a more geometric way, graphical way of doing this is the Mohr circle. So let's plot the Mohr circle. So when we plot the Mohr circle, what we have is sigma 2, which is equal to PR upon 2T, sigma 1, which is equal to PR upon T. And these 2 points are principal stresses. So the Mohr circle is going to look like this. We just plot a circle from these 2. Taus are 0 here. See, I am also in this case revising Mohr circle by doing this. I may not ask you the stresses which I said because the new theory, but this part is old. This is not new. Okay. So we plot the Mohr. Does everybody see how the Mohr circle is plotted? Taus are 0. So therefore we just look at sigma 1 and sigma 2. There are 2 points on the x-axis. And then we just draw these 2 points. So now, where is the maximum shear stress? This is the tau max in the plane of, which plane is this? Theta z. the sigma theta and theta z. In that plane of theta z, this is tau max. And what's the value of tau max? It is sigma 1 minus sigma 2 divided by 2. So this is PR by 4t, because sigma 1 minus sigma 2 is equal to PR by 2t. So therefore this radius, this is equal to PR by 4t. Now my question is this the maximum shear stress this cylinder faces, or is it something else? We have looked at the R, we have looked at the theta z plane. What is sigma R on the surface of the cylinder? Sigma R is 0. As we said, it will be basically P atmospheric. So either you call it as minus P, which is a very small thing, or let's take it as 0 if we take it as the gauge pressure. So sigma R is 0. Sigma 1 was sigma theta. So now if I look at the R theta plane, the two sigmas have been plotted. Sigma theta is sigma 1, sigma R is 0. So how does the Mohr circle look like in the R theta plane? It will be a circle of radius what? Sigma R is 0, sigma theta is sigma 1. Between these 2 points, if I plot a circle, how will the circle look like? So if I look at the R theta plane, this will be the Mohr circle. Sigma R is 0, sigma theta is sigma 1. So this is for the R theta plane. And what is tau max here? It will be equal to PR upon 2t. And this will be an out of plane. It will not be in the theta z plane. This will be in the R theta plane. That means it is out of plane of the initial element which we took. It is something not in the plane. And this maximum shear stress here is PR upon 2t. And therefore, as soon as the allowable stress, as soon as the pressure reaches a value such that PR upon 2t becomes equal to the allowable stress, the cylinder will start to fail. So what we understand from here is that when we did the in-plane analysis, we got the maximum stresses PR upon 40. But when we do the complete analysis, the maximum shear stress comes out to be equal to PR upon 2t, not PR upon 40. And therefore, that is the value which we should take for failure. And this is an example of how in a 3D problem, if we have to use Mohr circle, that is how we use Mohr circle, that we use, we can only do Mohr circle for principal stresses in 3D problems. If taus are given, we cannot use Mohr circle for the 3D problem. So we locate the 3 principal stresses. In this case, luckily, we are able to do it easily, the 3 principal stresses. And then we can plot 2 circles. Actually, there will be a third Mohr circle, which is this one, which will be for the RZ plane. But that is not relevant to our problem. But that would be the, so totally there are 3 circles which are there, one for XY, one for XZ, one for YZ. But you can only plot them if you know the principal stresses. And then you can plot it and get the value of the maximum shear stress. Okay. What we had done at the start of the course, we did only in-plane stresses. So in plane stresses meant one of them was 0. But there, if you account for that 0 stress, then the maximum shear stress will change. And it will be as shown here. So this is an example of how an out of plane stress can be more than the in plane stress. And this has to be used for design, not PR by 4T, but PR by 2T in this case. Is that clear? Okay. So now, as I told you, I will try to solve some problems in the remaining part of the class. Okay. So firstly, let me open this. This is the sheet which I told will be supplied to you. I have already, you don't have to bring a printout of this. I will be giving this to you. So this sheet is the last part of chapter 9 where we did beams and deflections. And this will help you in solving problems by superposition or otherwise. If you get the same configuration, suppose you get a cantilever with a load at end P, then you can directly look at the sheet, get the maximum deflection, get the slope at the end, and get the equation of the elastic curve. Okay, here everything is assumed to be positive. That means P is downwards, that is positive P. If P is acting upwards, then you have to put a minus sign in the formulas. So this is the equation of the elastic curves, and what we have given you are the curves for statically determinate beams. All these, you can only do it if it is statically determinate. If it is statically indeterminate, then we have to use superposition of these to get our solutions. Okay. So first one is a cantilever, second one is also a cantilever but with a uniformly distributed load. Now if you want to superpose 1 and 2, you see there could be situations when 1 and 2 have to be superposed. There is a point load as well as a uniformly distributed load. So then you'll have to superpose these, and how to superpose we will see in the problems to be done. But what I'm showing you is that this table is available, so therefore you don't have to remember all these. If you want to use the table, well, if I ask you to derive the equation of the elastic curve, then obviously you can't use this. And then you have to use the formula that d2y by dx square is equal to m upon ei. Derive the expression for mx and get the answer. Okay? So, but that is quite straightforward. So, this is just for you to be familiar. Also, if needed, j's and i's will be given. You don't have to remember the values of moments of inertia. So, for a circular section, for a rectangular section, if there is some other section, I will give the value to you. So, don't have to remember this. Everything else you have to remember. The formula for the bending stresses, the formula for the torsional stresses, that you have to remember. I hope you can, that's not too big. I think there are only 4 formulas or 5 formulas which come to my mind. One is that on epsilon ijk, epsilon ilm. Okay. The second formula is the Young's modulus. Delta is equal to PL upon AE. Okay. The third formula is the torsion formula. The fourth is the bending formula. And then for shear force bending moment diagram, if you think of them as formulas, then dV by dx is equal to minus W, dm by dx is equal to V. So those are the only things which I think you have to remember. Other than that, and there's one more. Relation between E, G and nu. Even I don't remember it. What E is equal to G, 1 minus 2 nu, something like that, whatever. If I were to write the exam, I would remember it. But I am setting the exam, not writing it, so I leave that for you. And as I told you, my logic for asking you to remember the formulas is at least some marks can be given if you put the right formula in the right problem. At least you state that formula, you will get some marks. So that is why, of course, for students who are doing well, you don't need to bother so much, but this is mainly for. Okay. So now, let's go back. Now, there are two types of problems. And here actually, I'm just taking the tutorial sheet. This also is there with you. So if you have seen this, probably you'll find this as a repetition. But just let's try to do one thing and then I'll solve one more problem. So this is a problem of trying to find, chapter 5, trying to find the shear force and bending moment diagrams. And also, why do we use this? From the maximum bending moment, we can find the maximum bending stresses, which should be equal to the allowable stress to be able to design the beam. Yeah. What is sigma? ALL. That is sigma allowable, the allowable stress. So that means that is the stress which the beam can take. There is a sigma ultimate also, and I have not covered explicitly the factor of safety. The factor of safety is basically a ratio of these two, sigma allowable and sigma ultimate. But here we will assume in all our problems factor of safety to be 1. So sigma allowable and sigma ultimate will be the same. Okay. So in problems like this, now here you have to find the shear force and bending moment diagram. Well, in certain problems it so happens that you have to find the reactions to be able to solve the problem. In others you don't. And if it is a statically indeterminate problem, then you will need chapter 9, you will need deflections to be able to find that reaction. Okay. So, for example, a problem like this, if you start, you actually don't need to find the reaction at C to solve the problem. Because you start from the left side and we have our formula, a force of minus P will create a shear force of minus P on all sections to its right. So when we start from 0 to A, the shear force will be minus P. And then there's a force of P acting at x is equal to A. So the shear force there will go down by another P. So it becomes minus 2P and it goes on till the end. And so obviously the reaction at the end. Now when you come to the bending moment diagram, there are multiple ways in which you can do it. One way is what we taught, that we look at P, then P times the distance from the cut gives us the bending moment. So there's a constant force minus P, so the bending moment will be minus P times X. Another way you can do it is you integrate the area under the shear force diagram. That will also give you the same thing. So it is up to you, either you use the integral or you use the formula. So we get minus P, and then if it's a linear relation, you go to the end at x is equal to A. What is the value? It is minus PA. So you draw a straight line starting from 0 up to minus PA. And then from A onwards, the bending moment will be equal to minus P times X minus P times bracket open X minus A. So you add the two and you get this curve. Again, you calculate the bending moment at X is equal to 2A from that formula, draw a straight line, and that gives you the answer. And then from a design purpose, you'll need the value of the maximum bending, which is minus 3P. If that part is. So these are all straightforward problems. Only thing which may get complicated maybe you have something like this. Now, again you have to draw the shear force and bending moment diagram. Now, first of all here, because there are reactions at A and B, and you have to start from one end, so you need to find RA and RB. So when you find RA and RB, the distributed load is replaced by its equivalent. So you put a force of equal to 25 into 1.8 acting at the center. And then you take Fx, sum of Fy is equal to 0 and sum of, if we want to start from the left side, we want to find Ra. So take moments about B is equal to 0. We do these and therefore we get the value of Ra and Rb. Okay. So, is this clear? How to find the value of Ra and Rb? Now, once you get Ra is equal to 62.5, then you start from 0 to C. Then V will be equal to 62.5x. 62, V will be equal to, sorry, there's a force of 62.5, V will be just 62.5. And moment will be equal to 62.5x. Is that clear? From A to C, that is what you do. Now you have to move from C to D. See, if you look at the figure, A to C, nothing special is happening. So the expression stays the same. Now when you go from C to D, there are two things which are there. One is this 40 kilonewtons is acting at C, and second is the distributed force. So let's have a look at this. So when you go from C to D, so you have 62.5, then you have a 40 kilonewtons. Now this distance is x, this distance is 0.6. So let's, and we have this force acting. So let's first write the expression for V. V will be equal to 62.5 minus 40, and then what will happen? Then this distance is x minus 0.6. So minus W times x minus 0.6. Is that clear? So you have to do in a point by point way. Okay. Next comes the expression for bending moment. Now bending moment we know plus P is P times zeta. Zeta is the distance from the cut section. So M is equal to 62.5 x minus 40 times x minus 0.6. And then how do we account for this force is W times 0.6 minus x. Okay. And where does this effectively act? This is acts at 0.6 minus x divided by 2. So zeta, now this is 0.6 minus x divided by 2 actually from both ends. But you have to be careful from which end it is, because in a triangular load that will make a difference. And zeta is the distance from the cut section. So that means we have to take W multiplied by 0.6 multiplied by 0.6 divided by 2. That's the distance from the cut section. Okay? Does everybody see this? So therefore, when I write this part here, the third thing will be minus W into 0.6 minus x into 0.6 minus x divided. Okay? So this is what the bending moment will be. Is that fine? So now one more thing about these curves. If I look at the shear force, so if you draw the shear force diagram, the first part is 62.5, then it comes down by 40, so it becomes 22.5, and then there is a linear distribution. Now, if you cross the line, if you cut the x-axis, that means there the moment will reach its maximum. Because V is equal to 0, that means dm by dx is 0. So therefore, that is the point where the bending moment will reach its maximum or minimum. So when we are drawing the curve, we first draw the moment diagram, we draw a straight line. Then we know that there is a parabola. And what I can do is that x is equal to, at the second critical point, I can calculate the value of the moment. And the point where it will become maximum will be the point where V is equal to 0. So then I draw approximately a parabolic curve between these two endpoints. And I know it takes like this, and then similarly I go to the end. For the last part, either you can move from the right side and get to your answer, or you can continue what we have done. Once we have crossed, then this distributed load, you can assume it to be acting at its center. You don't need to, you can just take the equivalent of the load and it is acting at the center, and then work out accordingly. So therefore, you get these answers like this. And see, again, the reason why V is equal to 0 becomes important is because the bending moment will be maximum or minimum at this point where V is 0. So you calculate the maximum magnitude there, and that is what will be used for design. Is that clear? So this takes care of an example from chapter 5. Now, let me take some example from chapter 9. So, let's see if this. Now, this is another similar problem, drawing the shear force and bending moment diagram. But here, the difference is there is a point moment, a concentrated moment acting somewhere. So here, explicitly in the shear force diagram, where the point moment comes, nothing will happen. But implicitly it changes things. Why? Because the reactions will change because of the moment. So implicitly it changes the shear force diagram, but when you go from C to E in the shear force diagram, the same trend will continue. The moment will not change the trend. But in the bending moment diagram, there will be a jump because of the moment. It is a clockwise moment, so it will make the moment go up. And you can see the solution they are given to you. If you look at the shear force diagram, once again, we start the shear force diagram. After some practice, you can directly write RA. Nothing is happening between A and C, so RA will continue. At C, you will go down by 3 kilonewtons. Okay, so here you worked out RA. RA was equal to 2.55. So at C, at the point, B, you go down by 3. That means 2.55 minus 3, so it's minus 0.4. And then from B to E, even though there is a moment at D, the shear force diagram doesn't change. And because they are only constant forces, it just stays a horizontal line. So we get the same diagram till E. At E, we go down by another 3 kilonewtons based on our convention, and then we go into a straight line. So this is what happens. So this shear force diagram, you could pretty much, if I give you the values of all the reactions, I think you should be able to just draw it directly. Okay. But the concentrated moment which is acting at point D shows in the bending moment diagram. In the bending moment diagram, first there is a linear part, and then there is a linear part which goes down. But because at D there is a clockwise moment, that means an anti-clockwise, a plus moment will come on all sections to its right. So we get, there's a jump at that point. And this jump is analogous to when we have a point force, the shear force diagram jump. So when we have a point moment, the bending moment diagram. There's a jump there. And then from B to E, once again the slope from B to D is the same as the slope from D to E. And then we go to 0. See, if at the two ends there is a supported ends, then the bending moment has to be 0. So we got it. Okay. So this is now in these two problems, the chapter 4 part has been added. That you have to find the either the modulus of the beam or the maximum shear maximum tensile stress or compressive stress which is coming in the beam. So you have to add sigma is equal to my. Otherwise it's all the same. So this I think should be straightforward. Well, so for it may be a repetition for some of you what I am doing now. So after drawing the shear force and bending moment diagram, you find the maximum value of bending moment. And because this is a rectangular beam, so you find the section modulus as bh square 6, and then find the maximum normal stress there. And then at that point, I think you're asked to find the maximum bending moment, and also that you can directly do. The next tutorial problem which was given to you is the one where you have to now, since the function has been specified, you have to use the relation dv by dx is equal to minus w and dm by dx is equal to v. So it's quite straightforward. If you do it, I think you can straight away get it. If there are any questions, please feel free to ask. I'm running through these because these are already given to you, but still I'm just going through you, just telling you some of the salient features. In this one again, all we have to do is draw the bending moment diagram and get the maximum bending moment diagram, get the section model. Now, let's come to one of the other problems, which is the problem on deflection. Now, in this problem, the problem says for the cantilever beam, determine the equation of elastic curve for the portion AB of the beam, the deflection at B and the slope at B. Now, this we can do using two ways. One is the way which it has been done here, that first we realize this is a statically determinate beam. You look at it because everything is given to you. The reaction at A and the moment at A are the two unknowns which you can find from statics. So first thing you should look in the problem is whether it is statically determinate or indeterminate. If it is determinate, then first thing which you will do is determine the reaction at A and determine the moment at A. So to do that, you write your equation of statics. So you have W is the total weight is W times 2A, which is acting at X is equal to A. And P is equal to 2 by 3 WA. So you do sigma F is equal to 0, sigma M is equal to 0, keeping in mind that there is a bending moment at A, which has to be put in because of the fixed end. And you get the value, it turns out RA is something and MA turns out to be 0. Then what you do is, you from A up to B, so you cut a section between A and B, call it X, and you find the bending moment at this point. Once you find the bending moment at the cut section, it turns out to be equal to half Wx square minus 4 by 3 Wax. Can everyone find this? You can use either the formula we have done or moment is 0. So you use this, you get the bending moment. And then this is equal to EI d2y by dx. So we work out, and then when we integrate this, two constants will come. Because it's d2y by dx square. And actually, to do this part, at x is equal to 0, we have y is equal to 0, and x is equal to 0, the slope is 0. So you get the values of C1 and C2 from there, and that gives you the elastic curve for AB, which is straightforward. Then to find that x is equal to 2a, next part was to determine the deflection at B and the slope at B. So then nothing else is needed here. You were not asked to find, the problem would have been slightly more complex if you were to find the slope at C and the deflection at C. Now what can you say for the slope at C? Slope at B, between B and C, there is a bending moment because of RA. So basically you'll have to write the expression for M between B and C and then integrate it twice, and then you'll get two constants, and those two constants will come from the fact that the slope at B and the deflection at B must be the same. So from there you will get the two constants, and then you can get the slope at C and the deflection at C. But another way of doing the same thing could have been using the figure and the superposition. And how we do that? Let me take up an example, something similar. I'll solve that problem fully for you. So Did I solve this in the last class or no? I'm not sure. I don't think so. Okay. So this is a statically determinate problem, not an indeterminate one. We'll do the indeterminate just a minute after. So here I'll just tell you, if you want to use the figure, you want to use the table to solve this problem. So this you will write it as, so this problem will be a sum of these two. So now here what we have is if I look at the table, I'll just go to the table. What I've done is I've divided this problem into two parts. Notice the reactions now will not be the same as in the total. R1 plus R1 prime will be the final R1. But we don't need this. As it turns out, what we do is I write what is my aim? Finding the deflection at D. So let me go to the table which is available with me. So in this table, let's see, I have, there must be one more. Yeah. So there is this number 6. Number 6 gives me uniform deflection at the same situation. And I have the elastic curve there. So, and all I need there is the value of W. I don't need R1 and R2. So from here, in the last column, I will put the value of X. And I will get the deflection at point D. Whatever X is there. Is that fine? And similarly, the second part is R1 and R2 with P. That means number 5. Now in number 5, what I get is at the point for X is equal to A, I get the deflection is given as minus P A square B square upon 3 EIL. Okay. Now A and B are given to me and the load P is given to me. So therefore I will get the deflection from table 5. And these two deflections when I add, I will get Y at point D. So I can directly use the table. Is that clear? And such examples are given in the tutorial sheet also. Now let's look at one more example of a statically indeterminate problem. And this one is slightly Now, when you apply this method, please be careful of the signs, because the signs are, if there's a load in the opposite direction, you have to put a minus. And the deflections also will go like whatever has been given. Now, suppose if we are given a thing like this. A beam between two fixed ends. Now here, if I draw the free body diagram of this beam, I will get, so this is at a distance A, it's not symmetric. I will get P. Is there anything else which will come? Moments. And actually, if you realize that there is RA plus RB is equal to P, take moments. So there are how many? 4 unknowns: MA, MB, RA, RB, and the number of equations we will get will be 2. One from the moment balance. So there are two. It's a double. You can call it as a double indeterminate. There are 2 unknowns here, which you cannot solve. So here, if you have to find for the deflection, so this beam is indeterminate of order 2. So you can treat this as a beam like this, where RC and MC are not known, or RB, what did I call it? B. So I should call it RB and MB are not known. So this I can write it as okay. And then what I can do is try to find the deflection at the point B. Delta B1 plus delta B2 and delta BC, delta B3. All these 3 I can find from the table. They will come in terms of RB, MB and P. The only known is P. Okay. So one equation I will get from here. Why? What is the deflection at B? It must be 0. So what I am going to do here is I will obtain. So this is delta 1, deflection here is delta 2. So delta 1B so this will give us, get one equation for in terms of P, RB and MB. Where will I get the second equation from? The second equation here is going to come from the fact that if this point is C, to find the deflections etc. for delta 1, how do I do? I first assume go up to point P, and from there I know that there is no moment. So the slope, it will be the beam will deflect up till 1 with the same formula, and then the slope will stay constant. So what I will have here, in fact, even determining delta 1 at B, so let's see, for load P, we find theta at C and delta at C from the table. So theta at C is equal to minus PL square upon 2y. This I am reading from the table. Do you want me to go to the table or can you see it on your own? I am first doing only the first delta 1. That means I am looking at this part. So this is C, this is B. And just for reference sake, maybe if I go to the table, I am looking at this table. The first table which gives me the deflection up till point P is minus PL cube upon 3I, and the slope at that end is minus PL square upon 2I. So we have gone only up to C. Okay? And then there is a free beam extending as far as deflection 1 goes. There is only a free beam. So this is what I have used here. And then so now what I have to use is YB at P is equal to Y at C plus theta at C multiplied by B. Okay, so this distance is A, this distance is B. So this is how I get the slope. So that means delta 1 is equal to for the force RB, I just have to look at the table and I get for the force RB, I get theta B is equal to RB L square upon 2 EI and YB is equal to plus RC L cube upon 3 EI. These are directly from the table for a point force. And for delta 3, I get theta B at for the moment is equal to MC times L upon EI and YC YB. So this is what I get for the moment. Now what do I have to do? I have got the three slopes and the three moments. What is the moment? What is the deflection at point B? 0. What is the slope at point B? That is also 0 because it's a fixed end. So I do the sum of the three y's is 0 and sum of the three thetas is 0. And that will give me MC and RC. MB and RB. Is that clear? So we can use superposition to solve these things, and you don't need to remember, you can use the graphs to solve them. So finally, theta at B is equal to theta 1 plus theta 2 plus theta 3 is equal to 0, and y at B Are there any questions on this? See, here the tricky part was, this one, that going from C to B when the point force was acting. What you have to realize there was the moment is 0, therefore the deflection takes a parabola and then it becomes a straight line. It is not that theta at C, delta 1 at C is not equal to delta 1 at B. You have to multiply it by that slope and by that length. Okay. So that's it. Are there any questions? Anything about the exam? Anything else? See, we have pretty much covered the solid mechanics part. There are many things which had to be done which we cannot cover. One is we have not seen the energy methods at all. Secondly, there is this concept of buckling. When you have a thin column and when you put a compressive load, then the column sort of crumples. And that is called buckling, which we have not seen at all. You want to see buckling example, you can try it. Take a Coke can or something, an empty can of Coke. You put your foot on that and just press the can from the side and you'll see suddenly it will crumple down. That is a phenomena called buckling, which we have not done at all in the course. Energy methods we have not done, and we have also not done any plasticity. We have only considered things in elastic limits. So, but that is the sort of, just to give you a feel of solid mechanics, how things go. We have done that. From the next class onwards, we will start fluid mechanics. So now, yeah. Uniform strength. That means basically the sigma allowable is the same for the entire rod. Okay. So I have not yet set the exam. Some people have been asking me, will there be theory questions? Will there be derivations? It could be anything. I have not yet set up. But let's see. It should be easy. It should be, if you have done the homeworks, you should be able to solve. Well, of course, exam has to be such that you have to differentiate. You have to get a distribution. I can't get a uniform distribution. So